Hi, good morning. Welcome back to another episode of Pollys Introduction to Computer Networks. So, the announcements today, as usual on Thursday, there's nothing new, okay, except for the links for the lectures in the Google Meet session. There's just one slight change that is changed on yesterday's announcement. So Poly is very often very ambitious about how fast we can go, but realizing that we couldn't. Okay, so this week the assignments doing will be just PA1 and quiz 4-5. Good. So let's go on. Start with the topics today. Hey, yesterday we talked about ADSL and cable, right? We kind of like cable because it offers a higher throughput, isn't it? But we are also concerned about using cable TV's network to send internet data because it's a shared medium. So we get higher throughput, but we might be sharing with many people, okay, and more than the factors we gain in the throughput increase. So it's not exactly ideal either, right? So we talk about this third kind, FTTH, fiber to the home. This one offers higher throughput and dedicated access. So this video about 5 minutes. Fiber to the home. This is the third access net technology. Unlike the previous two, where we kind of exploit certain existing infrastructure, telephone network or cable TV network, this one here builds its own network. And because the cable are all optic fibers, so it's called a optic network. And it's essentially the internet service providers, if they want to allow users to access internet using FTTH, they will have to go out there and build these optic links into the civil infrastructure. So there are physical contact, okay, through some cables between the central office to home. And so you see in this example, it's very clean between the central office to each household, just optic cable. Right. The only slight complication and boxes that are a little unfamiliar to you are these. First, optical line terminal. So this is a dummy device. What it does is just to collect signal and then convert them into digital bits. Okay, so that these internet data can go on natively through the edge router and out to the internet. Now, what's a little bit more interesting is this box, the optic splitter. We've seen this term, splitter, the third time. Yeah, at the physical level, these splitters are essentially the forwarders or the switchers. Okay, so signals gets forwarded to the right destination at this point. And signal gets multiplexed also so that they can go on further upstream. So splitter plays the role of demultiplexing signals so that it reaches a particular household, or multiplexing signals so that it goes to the central office. So its role is a little bit like the routers or switches at the core of the internet. So optic splitter here is a very important device for the optical network. In this example, we see there's only one level of it. In practice, there could be multiple levels, so that you could have a regional optical splitter, and then you could have another splitter here inside the building in case there are multiple households in your building, okay, also subscribing to the optical service. Now, these splitters, depending on the mechanism that's running in it, okay, depending on the design, could work differently. Okay, so two typical architecture for these splitters are these, PON and AON. So passive optical network. What it meant is that what's being done here is very straightforward. You just have mirrors so that you can reflect signals so that they go on the right direction to the destination. There's no signal amplification. But if you use active optic network splitter, yeah, these signals get splitted and amplified before they get passed on further. That is very necessary in case there are multiple levels of splitters along the way. as a signal as it travel longer distance, even though it's optic signal, it still decay. Okay. Now, in FTTH, yeah, the downstream or upstream bandwidth vary, but essentially the maximum capacity is much higher than the cable modem network, than the DSL network. Okay. In Taipei, very typical, you subscribe to services that's downlink 100 megabits per second, uplink 40 megabits per second. Okay. If you have special need, for example, if you are hosting web servers, then you might subscribe to 100 megabits per second downlink and 100 megabits per second uplink as well. Okay, so it can be symmetric, it can also be asymmetric in terms of the bandwidth in going in different directions. So essentially much higher rates, and it really depends on how much you can afford. Right? And nowadays these fibers can also carry telephone or television services. Okay, think about video on demand. So that is to carry TV programs through FTTH. And digital phone, okay, IP phones are one example. The trend is going towards that's just move to FTTH and then abandon the older legacy technology such as telephone, such as cable TV. So all content, including data, are transmitted over the one and only internet. One ring to rule them all.
All right, so we are all under the ruling of FTTH now. Okay, I guess you guys then all like FTTH, at least over cable and ADSL. Can you think of a drawback? I can share my observation. FTTH, expensive. Okay, so it costs money. Okay, and quite a bit more. All right, so let's move down. We have two more, which is Ethernet and wireless. So let's start with the Ethernet. This one is used very commonly in a company or on campus. It's surprisingly simple. And you can see in the video, it's only 1.5 minutes long. Very straightforward.
The fourth network access technology is Ethernet. Now this is something that we're very familiar with. All we need to do is to purchase one of these Ethernet switches, connecting our computer through the Ethernet cable to it, and this guy is connected to the edge router, then data can go out and in from the internet. Such a network access is typically used in companies and universities, okay, as they have direct access to the edge router. For households, we usually don't have access directly to the ISP's edge routers. Okay, so even though you're trying to connect your end systems through Ethernet cable to a switch, but that doesn't mean your access network is that Ethernet you're using. Be careful. Now, the rate these Ethernet switch is operating goes from 10 megabits per second 10 years ago all the way to nowadays 10 gigabits per second. But I think typically people use an Ethernet switch at this speed, 1 gigabits per second. And nowadays it's actually dedicated upstream 1 gigabits per second and downstream also 1 gigabits per second. 10 gigabits per second Ethernet is a little bit limited, and only those companies who are, for example, hosting a lot of data, then they need 10 gigabits per second Ethernet, particularly video providers.
All right, so that's Ethernet. Last is wireless access. Okay, as end users, this kind of access net is the kind that we use the most. Okay. Now, wireless network access, there are two kinds in general. One is for local area wireless access. The other is for wide area wireless access. For local area access, guess which one? Wi-Fi is local area wireless access. 5G, LTE, wider area wireless access. So this video not long, about 4 minutes, wireless network access technology.
This is the last access technology. It's called the wireless access. That's just how I refer to both of these wireless access technologies in a general term. Okay. The common characteristic is that all the devices, okay, on the same channel will share access. So the way it works is this. Devices sending wireless signals. It's picked up by the wireless base station and then passed on to the edge server and then further on to the internet, and vice versa. So these base stations, in the context of Wi-Fi in particular, are also called the access points. Now a little bit more about Wi-Fi. AL2.11b or G, this is actually a pretty old standard. I'm pretty sure that all of us are using AL2.11 at least N. Okay, so that's Wi-Fi generation 4 in another way. The bandwidth with Wi-Fi generation 4 is already close to 400 megabits per second. Okay, and the frequency band is no longer just 2.4 gigahertz, but also the 5 gigahertz band. Okay, that's why when you purchase a new Wi-Fi AP, you see that, hey, a lot of times when you set it up, you see two channels, one for 2.4 gigahertz, the other for the 5 gigahertz. The next major generation is Wi-Fi 6, which operates also on both 2.4 and 5 gigahertz for backward compatibility, in case you're still running AL2.11b or G. For Wi-Fi 6, the bandwidth actually go up this high, 900 and plus megabits per second. Really nice. I think in the next generation, that's called the AL2.11AD. Yeah, for this version of Wi-Fi, it's gonna operate at this frequency band, 60 gigahertz. It's super high frequency, super high data rate. In fact, 5G is also aiming at this frequency. So bandwidth is gonna be a lot higher. But you see also that the transmission is very directional, a little bit sensitive to the antenna design, okay, and very sensitive in case there's mobility. All right. Wi-Fi, interesting development there, AL2.11AD. The last one, okay, wide area wireless access actually meant, so 1 megabits per second, this is for 3G, okay. For 4G, we get slightly more than 1, sometimes go a few megabits per second. With 5G, you get easily tens of megabits per second and sometimes very close to 100, but only downlink. I have not yet seen any sort of measurements about 5G uplink bandwidth. It would be very interesting to know if you find any. Okay. But although these bandwidths we're talking about, downlink, uplink, it's increasingly higher and higher even for wireless access. But be very careful. As opposed to Ethernet, as opposed to optic, wireless is, after all, shared access. So these 400, 600, 900 or close to tens of megabits per second bandwidths are shared among all the users. And nowadays, we are probably connected to the network more through wireless access network, okay, than the wired one.
All right, so that's wireless. Okay, one characteristic is that it's now more shared, especially Wi-Fi, but it still depends a little bit on the hardware, okay, that you purchase. Okay, some Wi-Fi switches might allow a bit of switching. Okay, but the air that you are accessing to send signals is still shared. So 5 kinds, and we're done. This last video, very short, 2 minutes, is to summarize all these technologies, and I'm going to show you an example. At home, for example, we very often use a combination of these access networks to really send data to the internet or receiving data from the internet.
To sum things up, we've talked about 5 access networks: DSL, cable modem, and the very powerful FTTH, the optical network, to allow all the data, not just text-based, but audio-video data, to traverse. And it's replacing the traditional phone network, replacing the traditional cable TV network. We also talk about Ethernet access and the very popular wireless access. Now, all these 5 are access network technologies. These 3 definitely use a lot more for residential access. These 2 definitely use a lot more for institutional and mobile access. But nowadays, in a household, as the demand of using internet is on the rise and there are a lot more end systems are connected to the internet at home, having just one particular access network to enable multiple machines to go online at the same time is really challenging. So we have a hybrid access network in a way. In this example I'm showing, this is very typical home setting. Cable modem here is to access to the internet for the household entirely. But after the cable modem, we have what? An Ethernet switch here, okay, which is also called a router, which also runs the firewall functionality. This guy here would allow, for example, these PCs to connect through Ethernet cable to it. Yeah, these PCs are accessing internet using Ethernet switches. And the switch here can also connect to a Wi-Fi AP, and so that these laptops are accessing Ethernet through Wi-Fi. So in just this example, you have devices accessing the internet through different access net technologies. And be a little bit careful when I ask what is the access network for a particular computer. It can be relative, right? So this guy here is through Wi-Fi, this guy here is through Ethernet. But if I ask, how is this household accessing the internet? Yeah, the access network used by the household entirely is the cable modem.
All right, so access net. So we move on to the next thing about the access network, which is the cable, the medium we use to connect end systems to the core of the internet. Okay, so the physical thing that is enabling the access net technologies to work. Okay, so first video overviewing all kinds of cables we use and introducing the cable we use for Ethernet.
Here we're going to switch gear a little bit, but still about access network technologies. And so far, if you paid attention, each of these access net technologies operates on some sort of mechanism or protocols. They also operate with assumption on there's a companion physical media. This is important, just like the protocols are important to achieve a certain expected performance, typically achieving a really high bandwidth. Okay. Now, so let's go over these physical medias that work side by side with each of these access technologies. Now first, let's define some terms. Bit. These bits are propagated between the transmitter and the receiver. And between the transmitter and the receiver, whatever the media is called a physical link. And these links can be wired. There's a special term called guided media for it. If it's wireless link, then it's unguided media, meaning that the signal might just go propagating omnidirectional everywhere. Okay. As opposed to guided media, there's usually a copper wire or an optic fiber that the signal kind of just follow and being guided to travel through the physical media. Now, there are 4 kinds of physical medias we'll be talking about. First is twisted pair, and this is one of the commonly used cable for Ethernet. Cat5, this is very old for Ethernet that's 10 years ago. Nowadays, I think we're still using a lot of Cat5 cables, which supports up to 100 megabits per second and might be reasonably okay for 1 gigabit Ethernet. But if you purchase a 10 gigabits per second switch for intensive use, make sure you get these cables, Cat6, particularly 6A. This will allow you to have physical transmission bandwidth up to 10 gigabits per second. Just, by the way, it doesn't make sense to buy a really high-speed switch and the cable limits the speed, okay?
And guys, with that video, we'll work on quiz number 4. We were just talking about what? The Ethernet cables. So let me move to my whiteboard so we could draw on the slides. All right, so quiz 4. Okay, Ethernet cables. What I have here on the left is a table summarizing generations of Ethernet cables. All right, look, this is generation 5, Cat5, the category 5, 100 megabits per second cable. And we now have Cat6 and current state-of-the-art 6A. I think there are some other newer generations of cable already, but really expensive. And so as a cable, you probably don't want to purchase them yet unless it's necessary. Okay. So there are 3 generations of cable that I'm showing here. And these are what they look like. Okay, if you cut the outer edge open and turn the inside out, this is how they look like. Okay, now in these 3 generations of Ethernet cable, you see fundamentally they are different in the frequency band they use to modulate digital bits. So from the older generation, 100 megahertz wide, very narrow then, gradually increased to 250 to 500 megahertz. That usually means a wider bandwidth, you can modulate more bits. I recall ADSL and cable. So essentially what we're doing are modulating 0 or 1s onto these electromagnetic waves. Higher frequency or wider frequency band usually allow you to send more bits per second. And as a result, you see the capacity of these 3 generations of cable increase, right? From 1 gig to 10 and to 10. Now these technologies also, these 3 kinds of cable also differ in terms of shielding. Okay, so how the copper wires are wrapped around. Okay, I think there's a Cat7 that's using optic. Okay, so it's no longer using the optic copper wires. But you see, very simplistic look, right? Fancy. There are also some sort of tin or some sort of material wrapping around the cables. Those are to shield the noises so that the sub-cables won't be interfering with each other. All right? Good. And as a result, you see, the distance these cables, okay, allows to send data effectively differs, particularly Cat6 to 6A. It was 50 meter only, and now 100 meter. Wow, cool. So, to summarize, that was quiz 3. To summarize, you see, wider frequency and better shielding give you higher quality transmission. Okay. And quiz 4 is asking this. What you're seeing here is a network. Okay, quite complicated. We have FTTH, access to the internet. So ISP is internet service provider. Okay, so it's the company you pay a monthly fee to get fiber access. And this is probably your home company or a home office. Okay, and you have a high-speed switch here. And you do have 2 major servers, a video server storing video, and a NAS. It's a file system essentially, also high speed, okay, allowing you to back up hard disks, okay, or back up the video server. And then there are a number of desktops connected to the switch. Some use higher speed network access, and some use a lower speed network interface card. By the way, for servers, oftentimes you use very high internet access speed here. So high-speed network switch, high-speed network interface chip. And then there's one laptop accessing through Wi-Fi. So that is the environment. Q1 here asks, okay, given the above network, what cable would you use for link 3? Where's link 3? Right here. It's the cable connecting the switch to NAS. Which one would you use? And very important, tell me why. Q2, what cable would you use for link 6? Where's link 6? Here. Okay, so that is quiz 4. You are given 3 minutes. Okay, so I think it's quite straightforward. Cross-check your answer with your teammates. And you have 1 minute to fill the form. So overall, 4 minutes. It's now 10:46. Polly is going to come back to check your answer on 10:50. And now let's move to the score. And where is the channel you answer for quiz 4? Exactly, I see you guys busy and some of the teams provided answer already. Ow, really fast. W2, quiz 4 is the channel. Okay, go there and start working on it. All right, so hey guys, again, very straightforward, right? So you use 6A, no audio now? Interesting. I guess the other students, yeah. So maybe it's Nicholas on your end. Because usually when the video stream or audio not working, many of you will complain already. Yeah. Okay, good. Yeah, so video playing in the background. So some, yeah, not sure what might be about. Oh, okay, Anthony was asking a question. Okay, that's not technical. It's actual cost per meter for one of these cables. Imagine labor costs. Okay. Yeah, Anthony, that's a very good question. The cable itself doesn't cost all that much, especially Cat5. It's really, really cheap. Probably you can probably find people giving them out for free. But 6A, it's a lot cheaper now than last year, but it will still cost you. An exact price? Hey, it's actually dropping every month, so I know it's a little bit odd. We had a high inflation rate recently, but network equipment, their prices are actually dropping as they get old. So electronic is a very special type of products or commercial products, okay, that do not inflate equally with the general price. Okay, so I don't know the exact costs. Even if I know now, maybe next month it's no longer the same. But installing the cable, it's expensive. I don't know if you have experience installing the cables yourself. It can be a little bit tedious. But the labor cost and also depend on the region where you are. In Taiwan, it's growingly expensive as well, and it's rising like crazy. Okay, so hey, Anthony, I don't have the exact numbers, but I think the question are perfectly legit. The Cat 7 thing that you might find on Amazon.com, very expensive. Okay, how about you look it up and share with everyone? Okay, so hey, straightforward. For the NAS server, high-end 10 gigabits per second network interface, you want to use the full capacity of the server, then you need to use a cable that allows 10 gigabits per second transmission rate, throughput, or bandwidth. So I kind of I use these terms interleavingly. And so the only possibilities are what? Cat 6 and 6A. And because it's so far away from the switch, so you do want to use a long distance 10 gigabits per second cable, and that leaves us only the option of 6A. Okay. And for the desktop there, using just the 1 gigabits per second network interface, then the 5E is sufficient. Okay, good. And Sylvain and Jeremy, you guys are team 2. So next time, Sylvain, you can save some time typing up all the names and ID by just saying team number 2. All right, good. So I think that most of you come up with the same thing. Okay, I see Jingtao saying the same thing, and team 5 saying the same thing. 11 and 12, all good. So we go on, okay, to the rest of physical media. We just heard about the Ethernet cable. There are 3 more types of cables, or wireless cables, okay, coming up.
Next in line is coaxial cable. And this picture shows pretty much the structure of such a coaxial cable. What it meant by coaxial is that they have 2 layers, concentric, and these 2 layers of coppers allow you to send signals. And because having two layers, it kind of allow the modulator demodulators to easily cancel out the noises. And so data goes bidirectional on such a cable. A very primitive form of this coaxial cable was used by the legacy Ethernet. Yeah, by baseband, it meant that the bandwidth is really, really small, very low rate transmission, and it doesn't exist anymore. But then cable network picks it up, but enhance it somehow so that they can send multiple video programs over it, allowing multiple channels on the cable. And the cable exactly used by the cable network is HFC, the hybrid fiber copper cable. Oops. And the third is the fiber cable. Okay, so this is entirely glass-based fiber, and the bits are being sent as pulses. Okay, like that. It works in a very high speed. You can go up to hundreds of gigabits per second. These high-speed fibers are oftentimes used by also the internet backbone, where lots of data are being exchanged. It's also used by the data centers, where there are always high-volume data that needs to be stored or retrieved. These fibers, as we heard, FTTH, some of them slightly lower end is used for residential access as well. And they are very high speed, partly because it's very low error rate, because they are more resilient to white noises, background EM noises. The last media is the radio link. This one is very special. It is in fact the one that's used by all wireless and network access technologies. So what's listed here are just a few examples. Terrestrial microwave operating at about 45 megabits per second maximum. Wi-Fi, well, depending on the version, could be lower, 10 megabits per second, or half of 100 megabits per second. Wider area wireless access, 4G, for example, goes up to a few megabits per second. 5G is now tens of megabits per second, okay, with the potential going higher than 100 megabits per second. And satellite radio. Yeah, the bandwidth range spans wider with satellite, probably because of where the satellite is exactly and the technologies being implemented on that satellite. It can go from kilobits per second to 45 megabits per second. But one common feature is this. For satellite links, end-to-end delay will always be much longer than all these other wireless link access. Now, as to exactly how long the end-to-end delay is, it really depends on where the satellite is. For geosynchronous satellites, which sit higher above above Earth, the delay will get longer. The low altitude ones being lower, then shorter end-to-end delay. So, radio links, very special. Essentially, we are sending bits through these electromagnetic waves. There are no physical wire, so it's called unguided media. Data can go bidirectional, well, in fact, all directional. Which is a good and a bad thing. If you think about the propagation of these electromagnetic waves, it can be influenced by environmental effects. Having objects around, the objects can obstruct further propagation of the electromagnetic waves. And some objects might reflect, these waves as well. And the waves can be interfering with each other, coming from different sources, or even coming from the same radio source. It's called the multipass effect. So physical media, radio, it's very convenient, but you see the challenge of transmitting signals through these magnetic waves. You see also generally the wireless links, the maximum capacity usually lower than the guided media's capacity.
All right, so that's all that's about Internet Edge. And starting from this point, we'll be moving inward further into the core of the Internet. Okay. Before I play the video, let me try to address a couple questions during the last video. So Zachary was asking, if using a cable that's not enough range, okay, for example, using Cat6 instead of Cat6A for link 3 there, what would happen? Would the data transmission be slower, or would it not work at all? Okay, that's a very good question, Zachary. Usually it's slower. Because I say longer than 55 meter. If it's about 60, 70 meters, it might still work. So, that number, 55, is just a little bit loose, and it's set so that people are more sure that if it's within 55, it will work. But other than that, we don't know. Okay, so the closer to 55, the better the Cat6 cable will work. Now, the way it works is also a little bit more like this. If it's closer, then the loss rate, because we modulate the bits on the electromagnetic waves, and it decays and it reflects, and there could be noises. The chance is higher if you transfer a longer distance that you get some misinterpreted bits. So it will be slower in a way that there will be slightly more error bits that will take time to recover or retransmit. And another question from Nicholas. Okay, I guess you now have audio. Good, good for you. Voltage line. Ooh, 440. That is super high voltage. Okay, if it's nearby, would it cause a problem to the optic fiber? That's a super good question. Okay, if it's copper wire, I think it's very likely and really bad influence. If it's optic fiber, it's very directional. Okay, so I'm not quite sure about the inductive coupling. Okay, that might occur. I think for optic fiber, optic signals, it will be more resilient, a lot more resilient. But for all the other copper components, okay, across the wire, those components will be influenced. I think in the end, it might influence the end-to-end performance, but not a particular segment. Okay. I think it's just a lot more resilient. I'm not quite sure it's no influence at all. Okay, good. If you understand induction coupling, it takes certain material to couple better, and it also takes certain material being placed certain way or composed, structured certain way to work well. I think arbitrary high voltage cable nearby to OFC, there'll be some influence, but probably not that much. But it's still dangerous having a cable, okay, next to an optic fiber or any other cables. All right, and hey, that's all the question. And let's play the first video, 3 minutes. It's an overview of the core.
As access network is concluded, let's move on to the next component, the network core, which is a mesh of interconnected routers, as I'm trying to highlight here in red color. So you see a bunch of routers very well connected to each other. By well connected, let's see, if you count how many connections this router has to the rest of the internet. 1 here, 2, 3, and 4. 4 connections. Look at this one. How many connections? 1, 2, 3. Look at this one. It's an edge router, all right, but how many connections it has to the rest of the internet? 1, 2, and here, 3, 4. But if you look at a end system, such as this one here, how many connections it has to the internet? Just one here, through the Wi-Fi AP. Look at this PC here, only one. One very clear distinction between these routers to all these end systems is exactly in the connectivity, the number of connections they have to the rest of the internet. For routers, very oftentimes you see more than 2, including 2 connections. For end systems, just one. And the reason that the routers oftentimes have more connections is because their role are just to transfer data. So it takes us to this very fundamental question. How do we transfer data in such a well-connected mesh network? In general communication network design, very general communication network design, there are two major mechanisms. First, circuit switching. Second, packet switching. Idea is quite straightforward. In circuit switching, from the source to the destination, let's build a dedicated circuit, and this circuit is going to be reserved through the entire time of communication, so we could just dump data in, and the performance is guaranteed. And this is the mechanism used by the traditional telephone network. The other technique, packet switching. Instead of allocating resource, creating a dedicated circuit, let's just use the entire link capacity and let's send data out no matter what. But we cut the data such that it's sent one chunk at a time. And to call such a chunk of data, we have this term called packet. All right, so it's almost like a package, but packet means also a little package. Okay, so we send data in smaller chunks, but use the entire link capacity. Okay. And to tell you ahead of time, internet or the data network is taking this packet switching approach.
All right, so an overview of the core, and it's a perfect timing to take a break because there are more content coming up and a little bit more intensive than the XSNet and XS Media. So let's take a break for 10 minutes. It's now 11:08. We'll resume lectures 11:18. All right, so let's resume lectures. It was a break. Okay, so we'll be restarting. So in the last video you heard before the break, we see how the core could operate. So there are two models, right? One is to reserve resources, establish a circuit before sending data. The other is what? Go ahead, send data, okay, without any reservations. But you send data in a way that you send smaller segments of data at a time, one packet at a time. Okay. So these are the two models. The first one is called circuit switching. The other is called packet switching, right? Circuit, packet, keywords. So the first video coming up in the second hour is this. Let's talk a little bit more about how circuit switching works.
All right, now let me elaborate circuit switching a little bit more. This is the familiar network. But this time we see on the network there are two circuits. The red circuit connects this end to this other end. Similarly for the blue end. And to establish such a red circuit, which is also called a call sometimes, and the time it takes to set up such a call or such a circuit is also called the call setup time. Okay. And the reason that I need to mention that term is because that takes time, because resource reservation is required going from one end to another, which means this is the first link on the circuit. We need to reserve a certain amount of bandwidth to guarantee that data gets transmitted without any loss or delay. So you reserve link bandwidth for the call. Data is going to go through a switch. This is the first switch. On the switch, memory, CPU, buffer space will also need to be allocated and reserved. So that is what I meant by switch capacity here, to guarantee that the packet will not experience delay and not experiencing any loss. Similarly for the second hop, for the third hop, fourth hop, fifth, sixth, seventh, and eighth. When all 8 hop, link bandwidth switch capacity reservations are done, then you build a circuit. But then you see, as Polly was describing, this circuit here, resources are all dedicated. When data are being passed through, no delay, no loss. Really nice. And we call that circuit-like performance. That implies delay and no loss are guaranteed. Low delay, no loss, guaranteed. Similarly, for the blue circuit. And this is really nice because zoom into this segment. This segment here shared by the blue circuit and the red circuit. The two of them, although packet or data will be going through, but these data will not interfere with each other, not incurring delays to each other, and not collide to each other. No packet drops. These days, where we do online meetings a lot, having live YouTube channels a lot, we really like to have this circuit-like performance. This way, we don't have to worry that the internet is going to go bad and the live stream is going to break at some point. Nice. Because for certain applications, we do need this type of quality of service. But, you see, establishing the red circuit, we need 8 hops, and each hop takes some time to reserve resource. So there's quite a bit of call setup time involved. This is the downside of circuit switching. Another downside is this. The way we are allocating or reserving resources over the entire path from the two ends of data communication is more. We divide the link bandwidth into smaller pieces. We divide the switch capacity also into smaller pieces. And once we do that, we allocate individual pieces or combinations of pieces to an individual circuit or individual call. But once you do that, if there are no data being sent between the two ends, that piece of resource will then be idle. If you think about it, in a way, it's a waste of resource. If the two of them ask for resource and a call established, but they're sitting doing nothing. So not very good utilization of resource. So this is the second disadvantage of doing circuit switching. Now, speaking on dividing link capacity into pieces, there are multiple ways of doing that. First one is called frequency division, the other time division. This is the second time we see the term FDM. Where did we see this? Yeah, cable modem. We divide cable modem capacity. We divide the cable network link capacity into what? Pieces by the frequency band. This is a very different flavor. Okay, it's dividing the link by the time. Let me illustrate. The example on the top is doing FDM, where we divide the entire frequency band there to 4 users in equal division. So, full frequency band, 1/4 to the blue user, 1/4 to the green user, to the yellow user, and the pink user. TDM works this way. Instead of dividing the frequency dimension, let's divide, okay, in the time dimension. So with these time slots, we allocate the time slots in a rotating fashion to the 4 users like this. Blue, green, yellow, pink, blue, green, yellow, pink. Yeah, it's rhythmic. That is exactly how TDM works. With a good rhythm, with well-synchronized time, the 4 users can send data one after another. Very orderly. If we have more than 4 users, how do we do that? You see, we could further refine the division into, for example, A parts. That way we can accommodate how many users? A users. Similarly for TDM.
All right, so you see, there's a lot of work being done before you can send the data, right? Reserve the resources, but once you reserve the resource, establish a circuit, the delivery is pretty much guaranteed. Okay. There was a comment, I would say, from Solo-Fi. Wouldn't it be hard for circuit switching to re-establish the connections if a node stops working? Yeah. If there's a switch in the middle that's broken and come back on, yeah, all the connections going through that node will need to be re-established. Okay. And Miguel is asking, do we experience any delays in TDM? That's a very good question. There is, but just a little. And during the transmission, very little. But to establish a connection, that delay might be significant. Okay, so Miguel and Lo-Fi or the class, think about making a phone call. Right, we dial a number, that's the destination you want to reach, and so the phone network is trying to establish a connection. And so during the time before the connection is really set up, you are waiting. But once you're connected, you talk in real time, very interactively. So the actual delay after the connection is established, very fast. Okay, good. So that's the spirit of circuit switching. You see that it can be good and bad, right? Initial delay long, but afterwards, very short and somewhat guaranteed. Okay, so that's, go through an example, a quantitative example, so that it's a little bit more clear in how you assess the delays. So this video is just the starting part of the example, so it's about a minute.
To make sure you pick up circuit switching and how it works, let's see if we can work out this problem together. The question asked is, how long does it take to send a file, this big, from A to B over a circuit switch network? And in this network, all the links have the same capacity, 1.536 megabits per second. And each link is divided to 24 parts using TDM. And meaning that circuit between A and B only gets 1 slot. And the presumption is that to establish the end-to-end circuit between A and B, it takes this much time. All right, so how long does it take entirely to send the whole file through? Let's work on it.
Okay, so let me go to the whiteboard and see if we can work on this together. This is the exact example shown in the video. So we have 640K bits to set. Okay, So we want to establish a connection between host A and host B. And in this network, every link is this fast. And it runs TDMA, and each connection gets a 1/24th, okay, of the time. So that is also saying we get only this much speed, okay, for the data we want to send. Now, how much is this? Okay, hey guys, if you have a calculator, so sorry, I need to do this. So guys, you can also try to do the calculation on your end and see who come up with the answer first. 1/6 divided by 24. Yeah, so I have here that this is 64 kbps. It's 0.064 mbps, which is 64 kbps. Given that we have 640 kilobits to send, it will take us 10 seconds to send the whole file. But is that all the time we need to take to send the whole data when we started the initiation? No, because we also have half a second established time, right? So it's not just 10, it's 10.5 seconds, isn't it? Exactly. So you're following. Very good. Okay, Haley, Zhenyu, Wu Mingshi, yes, you guys are all right. Okay. Oh, sorry. So I'm actually writing out of the board here. So 10.5 seconds. Okay. So 10 seconds just to transmit data, but there's also half a second to establish the connection. Yeah. Oh, Yang, you're also correct. So circuit switching. Now, the feeling is quite clear, right? You do a lot of things ahead of time before sending data, but afterwards it's a guaranteed thing because resources are all reserved. There's no uncertainty, okay? And calculation of how much time it takes to do anything, straightforward. Now let's try and figure out packet switching. That's the other model, okay? And this first video is to overview packet switching, about 4.5, or actually about 5 minutes. Okay.
Now let's discuss more about packet switching. The mechanism is very simple, right? We simply cut the data into small packets, and as the link is available, pass it out. So each of these small packets will go on the link in full bandwidth. So if you consider L being the size of the packet length, and R being the link bandwidth or the link rate, the delay, this being small, this being large, to send a packet very small. This is one advantage. And then think about this: if you get two users, A and B, both are generating data and both are sending these packets out. If A is idle, not sending, and B comes up with data, B can send out, no problem, and in full link bandwidth. Similarly, if B is idle and A has data, no problem sending out. So there's no such a situation in circuit switching when B allocates all the resource, gets all the resource, and A having data to send, but A didn't get any resource as a result. B sitting idle, occupying all the resource, and yet A having lots of data wanting to send, not getting anything. Okay, so there's no idle waste there. Last is maybe a little bit less obvious. You see, bandwidth is used as full, so there's no need of dividing the link bandwidth into pieces. So the mechanism is also simple. Okay, being simple, there's no idle waste, and there's no call setup, resource reservation process required. Okay, packet switching can potentially be very efficient, especially for short data streams. Think about the resource reservation delay, the call setup time. It can be pretty long, and if you have very short data stream, then, hey, the overhead relative to the entire need of sending data is high. So you can probably imagine now, data network, internet. At the beginning, we were just sending really short emails. It doesn't make a whole lot of sense just to send an email and you go all the way to set up a circuit. So another advantage of using packet switching is also because of the user demand. Now let's look at what's wrong with packet switching. First of all, we will have resource contention because there's no reservation mechanism. What if A and B, they all have a lot of data to send, so the resource demand is beyond the available resource. So we call that situation network congestion. In that particular situation, packets will have to queue up at these routers and wait for link queues. So you see here, wait, the keyword. Delay here to transmit a packet is sure, but there could potentially be wait that is a little bit uncertainly long. Okay. And hey, packets will get queued. What if there's not enough space in the queue? Packets also get dropped. So in packet switch network, we do have substantial delay. We could have substantial packet losses. One big disadvantage. Another disadvantage is here. This one is a little bit subtle. In packet switching network, there's no circuit being established. The way we send packet is that you forward it out on the link. The next router will need to pick up everything. So you need to wait until the entire packet is received. The next router will need to receive the complete packet before the router can further forward the packet. So this is called store and forward. So the router action there passing packets is store the packet first and then forward the packet next. So this mechanism here is determining how packets are moved, okay, one hop at a time. Meaning you have one of these L divided by R every hop, every router.
Yeah, so packet switching, it sounds great, right? At the beginning, there's no longer reservation needed before data can be sent. So once you have data, you can just, push it out as soon as you can. But you see that when everyone is pushing data out without checking whether there's enough network resource, you might have congestion. And there's this queuing delay that's unpredictable. Right? And so for every hop, every router the packet will go through, there's this transmission delay, L divided by R. So packet switching, it sounds nice and cool. Okay, no pre-scheduling, no pre-reservation, but there are downsides, these congestions. And this next video is to talk about the downside a little bit more, and you see how it's very serious.
So here let me illustrate the store and forward effect to the end-to-end delay. So consider this scenario, the source is over here. Okay, user typing up things and generating these small packets, 1, 2, 3. One router here in the middle and receiver on the other side. And each packet here the user is generating is L bits long and the link bandwidth is R BPS. So you see, to send this big packet over the link at this speed, this is the amount of time that's required. And a packet switch network, we need to store the packet entirely before forwarding. So entire packet needs to arrive at the router before it can be transmitted further. The end-to-end delay will be what? 1 L divided by R for this hopping. Because this guy, to send it out, it requires L divided by R. This router here receiving it waits until all is received. And then what? Send it out again. That's another L divided by R. So if L is 7.5 0.5 megabits per second, R is 1.5. You see each hop, 5 seconds. 2 hops, in this case, how long? 10 seconds. 3 hops, the longer, the more hops you have, the delay of sending the packets longer. This is different from circuit switch network. Bits can be streamlined. Okay, there's no need to store a bunch of bits first before forwarding it. Okay, that is saying that each bit arriving here gets out quickly, so there's no hopping. It's just the propagation delay and the transmission delay, L divided by R, from the first hop. This slide is to illustrate congestion. The scenario is A and B, 2 users generating packets, A generating green packets and B here generating blue packets. And you see these packets are generated as user A and user B are typing things up spontaneously. So green and blue, they will kind of bunch up or multiplex in a random order. Okay. Unlike in TDM, time division multiplexing, everything goes rotating, rhythmic. And this, okay, having some sort of spontaneous behavior in it is statistical multiplexing. Okay, so on packet switch network or on the data network internet, packet kind of, multiplex to each other randomly, spontaneously, depending on how they are generated. Now let me draw your attention here. The router. You see packets in case the outgoing link, bandwidth small. An incoming link here, this is 100 megabits per second Ethernet. This is only 1.5 going out. Chances very high, A and B, if both of them actively generating lots of packets, the packets will have to wait here in the queue before they get the link queues. And if there's not enough space here for the queue, the next one, the green one coming here, will need to be dropped. But there's no memory space to hold. And those packets waiting in the queue, it depends on how long the queue is as they comes in to the router. The queuing delay can vary. It can be a little uncertain. But transmission delay, the time it takes to go on this link is always the packet size divided by 1.5 megabits per second. And we use the full link bandwidth. So transmission delay here is very easy to get.
Okay, I don't know about you. Okay, I see from that video, there are actually multiple sources of delay in packet switching. Some easily calculable, but some you don't know, right? Especially the queuing delay. And the packets kind of, compete with each other, bunch up. There's no regularity. So in a way that in packet switch network, once the packets are out on the network, well, it's a little bit hard to say whether they're going to reach the end, and it's also a little bit hard to say when they're going to reach the end. All right, so there are comments again. SSE was saying that are the packets treated as FIFO? In that example, yes. Okay, we are treating it in FIFO. Thank you, Solo 5. But in real internet, there could be certain routers that treat the packets coming in, even though in time sequence, but they might exit in different order. Okay, and that's covered in chapter 4. So bear with me. It will take us some time until towards the end of the semester you hear about these different queuing policy. Justin, is there a way to set priority? Hey, Justin, yes, there is. In fact, later, I think in chapter 4 again, you will see that in the packet header, in each packet, there are 2 parts. There's header and then the body. So body is where the real data coming from the end users, okay, whatever we type up. Hi, how are you? So those text messages are in the body. Then there will be some information in the header indicating how we are going to send the body. So those are the control fields in the packet. So one of those fields will allow us to set priority for that body of data. Okay, so that's also going to be in chapter 4. All right, okay. Now let's move on. We're still in the overview. I know you can't wait, so maybe I can speed up. In fact, starting next week, we'll speed things up, particularly the speed of the lecture up 10%, and then gradually more. All right? So next, let's compare CSPS. This is the core of the internet. There are two different models. CS, you might like it, you might not like it, but it's, deterministic. PS, you might like it, you might not like it, and it's a little bit unpredictable. Okay, so but let's try to compare these using one quantitative example.
Here, let me use an example to illustrate. Packet switching actually outperforms circuit switching when there are more users, and each of these users are not exactly very active, sending short messages only each time. All right, so scenario is very simple. Okay, we do have a network of end users, and they're behind this router. Going out of the router is a very low bandwidth link, 1 megabits per second. And each of the users is behaving this way. When they're active, they do need a lot of bandwidth, 100 kilobits per second. But they're only 10% of the time active. In a circuit switch network, in order to satisfy these 10 users, and each at maximum requires 100 kilobits per second, so we reserve 100 kilobits per second to each of the users. And how many users we are allowed to reserve bandwidth? This is 1,000 kilobits, so we can only allow 10 users, okay, 10 circuits. But in packet switching, you see, the users are only active at 10% of the time. Consider this scenario. If we have 35 users, right, the only situation that these 35 users will have trouble sending data out is when there's at least 10 users being active at the same time. So what is the probability of these 35 users and more than 10 of them being active at the same time? If you do the calculation, you'll see that it's very low. So 99.9996% of the time, in packet switch network, 35 users will do well. No trouble. So if you do have a lot more users and each of the user needs just a small portion of time to send data, which one would you pick? Circuit switching or packet switching? It's quite obvious, isn't it? And oh, by the way, anyone here knows how to derive this value? The probability of 10 of the users being active at the same time, given the active rate is 10%.
All right, so that takes us to quiz 5. Before we start quiz 5, okay, think about which one do you like better? Circuit switching, packet switching, given that example. All right, good. So quiz 5. We now know circuit switching is like this. Okay, we reserve a portion of the bandwidth ahead of time for the data. Okay, so if we compare this sending data to transferring water, okay, it will be like building the pipelines first before we start dumping water into the pipeline. Okay, and data will water will flow fluently through the pipeline. Now, packet switching, we know it's actually go ahead and send packets, okay, and they will be mixed as they are passed over the network. Now, in terms of transferring water, then it will be a little bit more like putting the water in buckets and having quite a few people there lined up and passing these buckets around. Okay, yeah, transferring data, transferring water, you find that there's certain analogy of doing circuit switching as well as doing packet switching. Or in the water transfer case, it's bucket switching. So think, Q1, which principle between these two, circuit switching, packet switching, these two principles, do you think the car network follows. Okay. And why do you think car network is more circuit switching or packet switching? And what about train network? Is it more packet switching or circuit switching? Why? And hey, I just asked you, right? Given that example, do you have like a certain intuition which of these principles you prefer? So Q3 is asking exactly that. Which one do you like better? Circuit switching, packet switching, personally? And share why you like one of them better. All right? And this one is a little bit open-ended. Try to find your team member and strike a discussion. You guys will have 8 minutes to discuss, okay, and 1 minute to input the data. All right, we are now at 11:50, so Polly will come back to check what you guys come up with. 11:59. Oh, by the way, hey, let's move to W2 quiz 5. Hey, wait. Oh, team 9 has already an answer. That's really quick, okay? But hey, guys, the rest of you, feel free to come up with your own idea and argue for your idea, all right? As long as the answer to the why part makes sense for your choice, you're fine. So let's come back at 10:59. Okay, maybe it will help the other teams to go on with the debate. So Team 9 says here, I like package switching more because it's more flexible. Okay, from that example we went through, it is more flexible, right? It can accommodate more people, more user, more packets. So would you, I mean, hey, it seems to be a good thing that more of us can participate, given limited resource, isn't it? But Team 1 says this, okay? I like switching because it seems more consistent. Yeah, isn't it? Because when we do packet switching to a degree that there's contention, then, well, many of us would get the resource, but a few of them won't. And those will feel, oh, it's not fair. isn't it? Okay, go on. Guys, discuss. Okay, time. Yeah, so we see most of you say the car network, it feels that it's a little bit more like the packet switch network, right? First of all, it's smaller units, and once it go on the road, it just travel around. Okay, it can take different routes. And you know what? Other cars might come and you could have contention. And you know, at certain intersections, you need to wait a long time. Hey, queuing delay. Train, it goes on a reserved track. You need to build those tracks before the trains can travel on them. So that does sound very much like a circuit switched principle of transferring something. Okay, I think you guys have all got it. So first, get a sense. Circuit switching, reservation based, reserving things. Packet switching, opportunistically use the resource we have. And something that I find interesting is this, okay? Most of you like packet switching because it seems that it can serve more people. But there's a very interesting argument about using circuit switching, in addition to being more consistent, predictable. Look at this. Team 11, Matthew here says, he likes circuit switching more because it's more energy efficient. Wow, okay. Well, looking at this, I thought it's interesting, but then Team 14 explained exactly why. Okay, Team 11 thinks that doing circuit switching will be more energy efficient. If you think about cars and trains as vehicles to transport human beings, which one is more energy efficient? In a car, there are a lot of times there are just one person you're transporting, but in a train very often, right? One train ride, lots of people. Okay, so amount of energy spent per person you're transporting, more energy efficient. So I enjoy reading Team 14's post. It explains, and it's actually, Joshua, you're actually trying to draw an analogy of circuit switching, packet switching to car train network, and then thinking what's good and bad in car network versus train network, and then discovering issues, okay, in packet switching and circuit switching. It's a very interesting argument, okay, but I have to say, Josh and Matthew, I'm actually not quite sure doing packet switching, circuit switching on the internet, which one is more energy efficient. Because it has a lot to do with how these routers operate. A lot of times, even though there are no data on them, there are no data being transmitted, there's probably a base amount of energy that's required. If that amount of energy is not that different from sending bits, okay, then we might not really be more energy efficient sending data through circuit switching. But you know what? I love you guys' ideas. Okay, those are interesting posts that generates more discussion. Okay, so that's all the time we have for quiz 5. Okay, let's go back to the lecture, and I'll definitely come back to check on Team 6, Team 5's answer for quiz 5, but later. Okay, so what we will do now is to summarize circuit switching and packet switching, and none of these is a slam dunk, really, a slam dunk solution.
After the discussion trying to solve the quiz, what do you think? Packet switching versus circuit switching. Do you think packet switching is the slam dunk winner? Is data network, internet's way, always gonna win? Probably not always, isn't it? It's great for short bursty data, right? Short amount of time, but sending lots of data, because it promotes maximum resource sharing, and it's quite simple, no code setup either. But on the other hand, we do have congestion. Packet delay might be unexpected long, and probably worse, there could be packet losses. And so you need additional protocols, yeah, because of the way the very low level packet forwardings are designed. So we probably need extra mechanism at the higher layer to ensure data can be transferred in a reliable way if it's necessary. And what if we want to do some level of a guarantee, for example, to do video streaming? Can we achieve circuit-like behavior with packet switching philosophy at a very low level? Can we do bandwidth guarantee? Well, people have been thinking about it, and this is still a problem that's not quite yet solved. And this is covered in chapter 9, the multimedia networking chapter, later on in the textbook. And we unfortunately won't have time to cover this semester.
All right, so that was an overview of circuit switching versus packet switching. And you know what? Internet operates based on packet switching. Okay, so the next topic is to talk more about packet switching. So, hey guys, if you like circuit switching better, sorry, okay, bear with us, follow us, and learn how internet operates. The principle is packet switching. You heard earlier that we, instead of sending big packages, we send smaller packets. But how small and how large? Okay, is there like a size that's appropriate? So this video, about 4 minutes, is to explain why we want to send in smaller packet size. Okay, as to how small is the best, you'll be asked to think about it. Okay, so this video, 4 minutes, explaining why we want to send small packets.
The next few slides, they are still somewhat important, okay, but not strictly talking about packet switching, circuit switching, and the comparison. So these slides are to answer a couple important questions. We said that packet switching, what it does is to divide data stream into small packets. But why not large packages, right? We didn't really justify that. We kind of like that L divided by R. The time it takes to send one packet is small because this is small. And in case the link is really fast, then this is small. But if this is a little bit larger, well, not so bad either, isn't it? Well, think again. And this is the example that I try to use to set up the stage. And it's just a slightly extended version of the previous example where we have 2 hops only, just one router between the source and destination. The packet size 7.5 megabits and the link rate 1.5 megabits per second. And you see that L divided by R is 5 seconds. And because there are 3 hops, so this time, store 5 seconds, 4, store 5 seconds, 4, and 5 more seconds to store. Altogether, 15 seconds to send this packet L. Now, 7.5 megabits, large, right? Sending a large package like this over this 3-hop network, 15 seconds. Let's try dividing this large message into smaller packets and see how it will work. 7.5 megabits, let's divide them into 5,000 packets. This way, each packet is only this big, 1.5K. Link rate is still what? 1.5 megabits. So to send a small packet like this, it takes only 1 millisecond. Now, look at this. This is the same network, 3 hops. Each packet is now very small. And to send one packet, the first router will take 1 millisecond to receive it and then send it out. So 1 millisecond, 2 milliseconds, and only 3 milliseconds until the destination receives the first packet. And you know what? These links can work in parallel, right? Because router 1 here can be passing packet 1 while the source start passing packet 2. You are trying to do also streamlining here, except that the unit of the streamlining is a small packet. You see, why packet switching suggests small packets? Because it's trying to maintain the benefit of doing circuit switching. Unfortunately, we could not be streamlining bits, okay? But let's keep the packet small. Then we get to keep some of these nice properties in a circuit switch network. And having these links that can work independently is nice. We can pipeline or streamline the sending of the packets over the network. So each link works in parallel. And the overall delay in the end is what? 5002 milliseconds, only 5.002 seconds. If you recall earlier, if we send, okay, 5,000 small packets altogether, 7.5 megabits, each hop 5 seconds, and 3 hops 15 seconds. How much time are we saving? Big time, isn't it? This is why in packet switching, people always talk about cutting data into small packets.
All right, so that's the video about why we send in small packets. But if we send really, really small packets, just 1 bit at a time, why is that bad? It's actually not good. If you recall, Polly mentioned, right? A packet, there's a header part containing the control messages. That's a fixed size. The body containing the real data bit, just 1 bit. If that's 20 bits and this is 1 bit, you're sending 21 bits just to communicate 1 bit of real data. Okay, yeah, so that 20 bits in the header are overheads. Okay, so you have low efficiency transmitting, high overhead transmitting real data. So you don't want the body part to be too small. So you don't want the packet size to be small because the header size is fixed. All right, good. So I hope that's clear. You don't want the packet size to be big because that way you get long delay in the end. But you don't want the packet to be too small because you'll be spending a lot of time sending the header bits, not the real data bits. Good. So let's resume and discuss more about packet switching next week. Okay. And with that said, I say goodbye. Okay. See you next week. Oh. Okay, while we say goodbye, maybe I can answer Justin's question. Is there a single optimum packet size? Ah, I see. Yeah, you guys also have a nice weekend. It looks like it's gonna be beautiful given the weather, okay, out there. Okay, bye. Anthony, I'll come back to answer your question after all the byes, because otherwise my answer is gonna be flushed out real quick. Oh, okay. Bye. Oh. Oh, okay, so you know the packet header size. Okay, good. Yeah, so if you want to make sure that there's no error in the packet header, you want to add some error checking code. So a bit, you can actually do less parity bits, but then it won't catch as many error cases. So lo-fi. So you've taken error correction code course. Very good use of what you learned from other courses here. Cool. Very cool. That's a wonderful ability, association. Are you Taiwanese student? Because usually Taiwanese students don't associate that well. Hey, don't tell people that I say that. But hey, many of you can be trained to associate better. Welcome. Yeah, I do have quite a few Indian, because I can see from the back end of YouTube. I have more Indian audience, in fact. Okay, and I'm having more U.S. audience. I guess it depends on the school system. Sometimes universities in one region will start school or having midterms at some point, and I'll see a certain surge of viewership. Good. Hey, enjoy Solo-Fi, Mr. Solo-Fi or Miss Solo-Fi. Okay, bye. You're welcome to crushing anytime. Okay, so I'm gonna end the stream. Yeah. Okay, bye.